Okay, everybody, so here's what this unit called computer organization has kind of done for you guys. As we finish now the last part, this part 4 of this, the idea was to get a basic understanding of how the computer as a hardware device is working. So we know what it's like as coders. We give instructions and then it uses those instructions to do fancy things. But if we pull back to the next level, right, so we write code, okay, that's going to go to the machine. Okay? But at the machine's level, we know now that what's happening inside there is instructions are just a series of ones and zeros, which isn't really true because it's not really ones and zeros either. It's just electrical impulses or positives and negatives, okay? Or, you know, like magnetized, demagnetized, or a series of just switches. Okay? There's a cycle to this, right? We learned that the machine has that CPU, which is the brain that has a cycle within it that executes the instructions on that cycle. It keeps track of stuff in memory. And memory is also just ones and zeros, et cetera, et cetera. But now, if we dig even deeper, okay, into this, okay, how does it actually do stuff with the ones and zeros? Well, you guys know as coders that it really comes down to basically math, right? Like basically, if I give you a 0 and then I give you a 1, we can do stuff with those two numbers, right? We can mathematically, for example, add them, subtract them, multiply them, or divide them. But do I really need to do all 4 of those things? Not really. Because if this number down here is negative, then I can just add them, right? So in other words, out of these 2 math functions, adding and subtracting, I don't have to do subtracting if I can make a number negative, right? In other words, 5, that's a 5, minus 2 is the same as 5 plus negative 2. So I don't need to subtract if I can make stuff negative. Multiplication is actually just repeated division, or sorry, repeated addition, right? Like 5 times 3 is really 5 plus 5 plus 5, 3 times, right? So multiplication is repeated division. And, repeated addition. And since we just said that we can use addition to create subtraction, then division is really just repeated subtraction, which is really repeated addition of a negative. So it all comes down really to just this. So here's where we're at. All 3 years of computer science programming, and sitting in front of you right now is a box that just adds ones and zeros. That's all it does. That's at its core, all the computer actually does is just add ones and zeros together. So let's see how you guys would do if I said to you this. How would you do it? Okay. Well, just like regular math, we'll do one column at a time. What's 1 plus 0? Oh, okay, that was easy. What's 0 plus 1? Same thing, but now it gets trickier. What's 1 plus 1? It's 2, right? But how do we write 2? 1, 0. So in other words, we put a 0 and we carry the 1. Ah, carry. Then we have 1 plus 0, which is the same thing, 0 and that. Okay? So binary addition is actually pretty simple. Okay? And if this number is a negative, then I'm doing subtraction. So all of it is based on these simple switches happening there. And that's what this unit has been trying to get to. And what today's sort of also gets to is that sort of basic level of what's going on there. Okay. So let's take a look at our final part, part 4 today. First, we'll take a look at what the IB curriculum says you need to know in this unit. So it's another piece of this curriculum point at this part. Okay, so here's what we need to know by the end of this. We need to define the Boolean operators and, or, not. I think you guys know those ones, but here get some new ones. NAND NOR and XOR, which actually the cool kids pronounce XOR. XOR. Okay, construct truth tables using the above operators. So truth tables. And there's an example here. We'll come back to the example at the end. Construct a logic diagram using AND, OR, NOT, NAND, NOR, and XOR gates. So we're going to see what that is during today's presentation. It says problems will be limited to an output dependent on no more than 3 inputs. So we'll remember that the maximum number of inputs they could give you in a question is 3. The gate should be written as a circle with the name of the gate inside it. I'm not going to teach you that because I think that's the stupidest idea in the world. But we'll show you how it works in a minute. Okay. So all of this is actually based on mathematical laws, just like our regular math laws that we could describe as algebraic laws. But in the world of Boolean algebra, we don't have as many numbers to worry about. We just got 2 numbers to worry about. So if I flip back here, we've already started that. Here we're only worrying about 2 numbers. In regular math, we have to worry about 10 digits, and a massive amount of numbers, from like negative infinity all the way up to positive infinity worth of numbers. But really, it's just 10 digits. But as well, we had 4 basic math functions. We had the whole adding, subtracting, multiplying, and dividing. But in the world of Boolean algebra, we only have 2 numbers, not more than 2 numbers. And you'd think it's just adding, but it's actually not. It's not adding we're going to worry about. We're going to worry about different math functions in Boolean algebra. We're going to worry about AND, OR, and NOT. So that seems weird, but let's see how that might work. Like if I told you what's 0 plus 0, you knew what that is. But what if I told you what's 0 and 1? Or 1 or 0? Or 1 and 1. Now remember, this will give you an answer. What possible number of answers could there be to this question? Just 2, right? 0 or 1. So let's just take a guess right now. If I was to say to you, 0 and 1 equals, your answer can be either 0 or 1, so you got a 50-50 shot. Which would it be? So your answer would be 1, okay? 1 or 0, what would your answer be? 50-50, if you guess. Guess. 0. And 1 and 1. Come on, guess. It's a 1 or a 0. Just guess. 0. Congratulations. You got them all wrong. Every single one of them is wrong. All right, and here's why. Think of it in coding, like in an if statement. If I say if x equals 1 and y equals 1, do one or both of them have to be true with AND? Both. So are these both zeros? Nope. So the answer should be 0. Now with OR, either one of them can be a 1 for it to generate a 1. So 1 or 0 equals 1 because either one of them can be a 1. We're looking for the answer 1 being essentially true. What should this one be? Think of 1 as true. True and true is? True. Okay. Or 1. Okay, let's try it again. You guys disappointed me a little bit. Let's try writing it instead of 0, 1. We'll write it this way. True and false equals true or false equals false and false equals. What would you write? What would you write for this one? Oh, now you're getting fancy. What's this one? True. And this one? Okay. And basically, again, if I substitute a 1 here and a 0 here, it starts to make sense. Okay. So that's basically how the computer works. Is it uses, instead of pluses and minuses, it uses the ands, the ors, and the nots. Oh, we've got about the nots. You want to see easy. What's not true? What's not true? False. What's not false? There, you learned it not. That's the easy one, okay? Now, this is what Boolean algebra is based on. It's based on these simple things, and or not, okay, and ones and zeros. And then it uses notation to note this, okay? So we're used to notation in regular math of ones and zeros. But the way we do, for example, not, okay, is to use a prime symbol, okay? So not 0 is 1. Not 1 is 0, okay? In some computer science courses, they use an overline like this. I don't like that. I prefer the prime symbol, but watch for that. That might show up on your exam. I'm not sure. Now, if we don't know what the value is, we'll use a variable. Okay? Whoops, that's not supposed to be a 1. Okay? So there, I don't know what x is. X is going to be either a 1 or a 0. Whatever x is, its not will matter. So what I can start with right here is what's called a truth table. So in other words, this is the truth. Okay? So my truth table looks like this. Here's the value of x. Well, it could be a 0 or it could be a 1. So if that's true, the value of x naught would be a 1 or a 0. Right? Whatever x is, x naught is its opposite, or its dual. Very simple truth table. Okay? That's a truth table for when things are being knotted. Okay? And the symbol for not is prime or an overline. Okay, those are the two symbols you may encounter. Now, the next thing that's used in Boolean algebra is the and. Now, I'd say symbol, but I'm going to start using the word gate. Okay, the and gate. And here's how it works. Okay, I can have 0 and. Now, the symbol they use, believe it or not, is the same symbol we use for multiplication. So that could be an x, but we don't do that in algebra. It could be a dot. We don't do that in algebra. What do we do in algebra if we want to say 2 times x? How do we write it? Just 2x, right? So if I want to put them together, I'd do this. This means 0 and 1. Okay? And this would mean 1 and 1. Okay? Sometimes they will put an actual dot in between. They don't put an x, but that would mean and. Okay? That, however, has a different meaning in Boolean algebra. What and means, we will figure out through a truth table again. Okay. So let's make two variables, x and y. What possible combinations could we have? Well, they could both be 0, right? What other combinations could we have? Well, the y could be a 1 and the x could be a 0. Or the x could be a 1 and the y could be a 0. And what other combination? They could both be 1. By the way, do you notice any particular pattern about what I just did? It's the first four binary numbers, right? Now, if that's the truth, what would the result of x and y be? Let's think it out. 0 and 0 would be 0 and 1. No, 0. 1 and 0. And 1 and 1. 1. So with and, the only time you get a true answer is if they're both true, which is exactly right. That's the way and works. It worked that way with if statements, right? If this and this, they had to both be true. So only when both are true do I actually get the 1. Otherwise, I get a 0. Okay, let's move to the next thing. The next thing we want to learn about is or. Okay. Similarly, we can combine two things, 0, 1, 1, 1, or x and y if we don't know what they are. Now in regular math we have symbols. In Boolean algebra, believe it or not, the symbol they use to make OR, just to make it super confusing for you, is the same symbol we use for plus. That means OR in Boolean algebra. Okay? So this means the same as 0 or 1, 1 or 1, or x or y. Now this will make more sense once we start writing it out in a truth table. So let's do that. So the truth of this is, okay, if we have x and y, all the combinations, let's write this a little quicker this time, 0, 0, 0, 1, 1, 0, 1, 1, or the first 4 binary numbers. Okay, so the combination of x or y, let's see what it generates. What does it generate with 2 zeros? 0 or 0? 0. 1, or pardon me, 0 or 1? 1, yeah. 1 or 0? And 1 or 1? No, 1, you're right. Now in the OR, it's always generating a 1, except in one circumstance it's generating a 0. So this is kind of the opposite of the way it was working with AND. And think about it, that's the way OR generally works, right? This or this. Either one of them can be true, or both of them can be true for the thing to be true. The only time it's false is if both of them are false. So that's the way it works. Your basic Boolean algebra, not, and OR. Now, this is the symbols used in math for Boolean algebra. But if you hand this to an engineer or an electrician, and I know some of you guys took electronics, they can't build anything from this. They need an electronic symbol to represent what this is, and that's why I use the word gate, because they actually have little electronic gates that work with this. So when 2 inputs come into the gate, it knows what output to produce. In other words, if you think about it, I've got an electrical wire coming in and another electrical wire. And these 2 wires come into some device and something comes out. So in other words, I send it a positive charge and a negative charge. Does what comes out be either a positive or a negative? Or if I switch that, right? If I give it a negative charge and a negative charge, or all the different combinations of it. And you can also think of those positive and negatives as 1s and 0s. If this gate I gave them is an AND gate, then we know exactly what comes out of it based on the 2 inputs. We know what comes out of it. So for someone who's building electricity or electrical boxes, this is all they need. They just need a gate to determine what's going in and what's coming out, positive or negative. So here's what the IB said, if I jump back to the curriculum, is this is actually all you need to do. Is on a question like this, you actually draw it like this with a circle with the word AND in it, or a circle with the word OR in it. I don't want you to do that, because that's wrong. That's just horrible. Here's the way the gates actually look, okay? This is what an electrician will tell you, okay? Or an engineer. The NOT gate looks like this, because the NOT gate just has one input and it reverses it. It has a little triangle with a circle on it. That's what a NOT gate looks like. So if I send it a 1, out comes a 0. If I send it a 0, out comes a 1. That's how it works. That's the way the gate looks. With an AND gate, okay, we're going to have 2 inputs, right? 1, 0, 0, 1, 0, 0, 1, 1. The way the AND gate looks, is it looks kind of like a half circle or a plug. Some people call it a plug. That is the AND gate, okay? And then the OR gate has been described as the rocket ship. The way it looks is this, sort of like this, like that, okay? Have any of you who took electronics ever seen these symbols before? Because that's what they are. They are the AND, the OR, and the NOT gate. Okay, see how good you guys are. Let me give you a little Boolean expression here. just like a math expression. I'm going to say x and y or z equals 1. How would we draw this using gates? Well, knowing that that's not regular math, that's Boolean, I could write it in terms of words. I'd say x and y or z is equal to 1. Or I could use the word true there as well. Okay? How I would draw it is I'd have an x, a y, and a z as 3 possible inputs into this circuit that I'm building. I combine x and y using an AND gate. There, they're combined. And then the result of what those things are combined with combines with the z using an OR gate. So this is the same circuit, x and y or z. Now, what you may have noticed is this could have also been written a slightly different way. Okay? I could have also, let me just group that together. Oh, really? Oh, man. Maybe I'll just draw it in. Z right there. Okay. I could have also done it sort of backwards. I could have said, oh, I got x, y, and z. I could combine these two first. So y and z are combined with the OR. And then these two are combined with the x using an AND gate. So which of these two circuits is correct? This one or this one? Which do you feel is more correct, naturally? This one? Why do you think that? Are you basing that on the math you know? Because of BEDMAS? Do you think that applies in the world of Boolean algebra? It could. You're right. Okay? Don't overthink it. Your instincts were correct. Okay? ANDs are done before ORs in the BEDMAS of Boolean algebra. Okay, so let's see how good you guys are. Ready? I'm going to draw you a circuit. I'll make it 4. No. Hold on. Can you use words to describe what's going on in this? Or can you tell me what to write if I was to write this in Boolean algebra? Just start saying words. Don't overthink it. X or Y. Remember, that's OR. Yeah. And Z. So this and Z prime, which is? So in other words, all of this knotted, right? Yeah. That's it. You got it. Okay? Now that's kind of a hard one there, right there, but that's essentially what it means. Okay? That's the Boolean algebra. Now, do you need to necessarily know one that difficult? Well, if you remember what I showed you in the IB curriculum at the beginning, it's not necessarily. Okay? So the prime symbol in Boolean algebra means to knot something, to reverse the polarity. Okay? This can be applied to variables, so not 1 is 0, not 0 is 1. That's pretty simple. Okay? So not x is 1, not x is 0 when x is 0 or when x is 1. Or write it in a truth table, as we just showed you. Okay? That's the symbol. That's the actual symbol you give to an electrical engineer when they build these things. That's the symbol used to describe the NOT gate. Okay, the AND. Here, oh, this notation here, you may encounter that one. I forgot about that one. Some countries put that little hat symbol on there in between. I sure hope your IB exam doesn't have that. This one more commonly, but basically it's just the symbol we use to represent multiplication. In Boolean algebra represents AND. Okay? And then the OR, and this is also another, if they use that one, I'm going to flip out on the IB, but that's the way it works. So the OR gates that in that way. Okay? There's your truth table. So again, things to note about the truth table is with AND, there's only one instance where a 1 is generated, and with OR, there's only one instance where a 1 is not generated. Okay? Now, here's the thing. In Boolean algebra, everything has what's called a dual. So everything has its opposite. So the opposite of and is or, the opposite of or is and, the opposite of not is, well, not itself, okay? So anything you do to a 1 has an opposite effect you can do to a 0. That's the beauty of Boolean algebra. That's why the computer works so fast. It's because it's basically just two sides of the same coin. Everything has a dual and everything is valid in the opposite. That's your and symbol, that's your or symbol, which is hard to draw in PowerPoint, but I was able to pull it off. All right. So, there's your priority order, okay? Or your BEDMOS for Boolean algebra. That not is done first, then and, then or. So or has the lowest priority. And to be honest, this is not that difficult than regular math. In regular math, multiplication is done before addition, so don't overthink it. The symbols you use match up with the learning you've already done. Okay. So say that out loud. Not A and, no, no, try again. Not. A and B not, yeah, or B not and A. Right? You said A naught. It's not A naught, it's B naught, right? Means that, okay, or that gate. It does not mean that, okay, there's a difference. Okay, that's wrong. Okay, hang on. Say that out loud. Wait, I gotta freeze the screen. It's gonna pop up. Say that out loud. Close. Yeah, say it again. A or B and C, yeah. So A or B and C. Okay, could you see?
I haven't seen so many knots since Jethro Bodine did that. I don't know the reference there. They won't.
I know I did, yeah. So that's what it means. It does not mean that. Okay, there's a difference. All right. Now, complicated. Okay, can definitely get more complicated. Does anyone want to try that one? Anyone want to give it a try? How about I give it a try? A or B naught, or C and D and E or F and G naught. It's like poetry now. Wow. Now, anything in Boolean algebra can be expressed in words, like I just did. I just tried to do it in words, or in an expression, a Boolean algebra expression, or we can draw it up as a truth table. I'm not drawing that truth table, that's nasty. Or we can draw a circuit diagram to represent it. So let's try a practical example. Okay? A car has 3 sensors. Sensor 1, which we're going to call K, will generate a 1. The sensor turns on when the key is in the ignition. Sensor D turns on when the door is left open in the car. And sensor L turns on when you leave the lights on. The car also has a buzzer that will sound. In other words, it will turn on when it gets a 1. The buzzer turns on when it gets a 1. So the buzzer goes off if the lights are on when the key is not in the ignition, or when the door is open and the key is in the ignition. Solve this with a Boolean expression, a truth table, and a circuit diagram. Okay, so let's dive into this question. Here's what we know. We have 3 inputs, K, D, and L. Okay, so let's try and draw this up. So we have K, which is the key. So when the key is in the ignition, a 1 happens. We have L, which is the lights. And we have D, which is the door. Whoops. So if the lights are on, a 1 happens. If the door is open, a 1 happens. On this end, we have B, which is the buzzer. So the buzzer turns on when it gets a 1. What goes in the middle is the Boolean algebra that will determine whether or not we generate a 1 or not. So here's what it says. The buzzer goes if the lights are on, but not just if the lights are on, when the key is not in the ignition. Okay, so let's see if we can write that in. So if this is a 1, but the key is a 0, right? So how would I write that? So it's only if there's a 1. So will the buzzer go on if the key is a 1? Okay. So in other words, if this is a 1 and this is a 0, then we get a 1 over here, right? Is that right? Okay. Is that the only combination that will work for? Like if this is a 1 and this is a 1, it's a 0, right? that right? Well, no, I'm just asking you. We need to find what symbol would go in the middle there. Would it be and? Okay. So would that work if we put an and there? Oh, absolutely, we can put a not before there. So we can put a not right there. Would that work? Okay. So that's good. We got that in place. So let's see what the rest of this looks like. There's a hint. When the door is open and the key is in the ignition. So in other words, if the door and the key are both, so I have to bring this down to another wire down here. So this wire goes up here, this wire goes there. So now I'm combining the key and the door. And they have to both be on, right? So that's just a simple and. And we said it could be this or this. So now I can combine these two with an or. Okay? And that's my circuit, right? So I can combine the circuits together in that way to generate the actual mechanics of what an electrical engineer would do to build that sort of a sensor system into a car using those gates. Okay? You guys got it. There it is, right there. Okay? There's the actual algebra as well happening there. Okay? Now, that was a pretty tricky one. If we were to write out the truth table, it would look like this. So in all the instances here where everything's off, the buzzer would be off. Okay? Now, ways I could solve this as well is just like I'd solve in regular math. I could actually punch the numbers into the equation to come up with answers. So what would happen here? So in other words, substitute a 1 into this. And what would you get? So everything else is a 0. So first of all, k is a 0, but it's being knotted, which makes it a 1. And then I have 1 and 0. What's 1 and 0? 0. Okay, hang on. I think you guys are, I might be losing you guys a little bit here. I can feel a bit of a loss here. Okay, so hang on. Let me go back to that. L, K naught, or dk. L, K naught, or dk equals B. Okay, so we have the scenario of a truth table here of L, K, and D. We already did all zeros. 0. But in this case, what happens when I substitute a 1 in place of this? So everything else is a 0. Okay? So we'd use bedmass. This is done first, right? So it's this, 0, 1. Next bedmass, we do these two first. 0 and 1 is 0. 1 and 0 is 0. 0 or 0 is 0. We got our answer. Now we'll do it this way, 0, 1. Okay, we're going to have to find out that one. We're going to have to find out this one. We're going to have to find out this one, this one, this one, oops, and that one. Those are all the possible scenarios of this truth table. Okay? So let's take a guess what they'll be. I'll jump over to here and we'll fill them in. So that was a 0. Next one, guess, 0. Next one? Oh. Next one? Oh. You get a 50-50. Next one? Okay, let you think it out a bit. Let do the math. Oh, we got to debate. 1 or 0? 1. And finally? Okay. Now this is harder than the kind of question you can expect in general, but it's not too much harder, okay? The kind of question you might expect on an IB exam. But you haven't worked out these types of problems. So I think you guys are going to need some practice working on these. I'm skipping over it fairly quickly today, but this is the kind of stuff that you can do. Now, let's try another one. Convert this circuit diagram to a Boolean expression. So there's the circuit. How would you turn that into algebra? Okay, so think it through a little bit. Okay, take each piece at the end here. So at the very end, it's being knotted. So you have some giant thing that at the very end is being knotted. Okay, and just before that, you're having two things being ORed, right? On this side, what's being ORed? A and B. A and B or something being knotted. And what's being knotted is two things being ANDed. And what the two things are is B and C, but B's being knotted first. So it's not B and C. Okay? So this will take a little practice, but if you think that through, it'll look like this, right? Here's A and B. Here's B and not C. Then you knot this, so it's that, right? B and not C being knotted. Then that and that are being combined with OR, right? A and B or not B, not, and C. And then that whole thing is being knotted to generate X. That's pretty nasty, but that's how it relates. So you can actually work it out on a mathematical level or as an engineer on a circuit diagram level. Okay, now here's how it would work. If you generate these ones and zeros going into these gates, think about what's coming out right here. What's coming out right there? A 1. This is turning into a 0. So what's coming out right here? 0, right. So you guys got this. So 1 goes in, 1 goes in, 1 goes in, gets turned into a 0, 0 goes in. So now 1 comes out over here. A 0 goes into this thing, comes out a 1. So now what comes out over here? A 1 gets turned into a 0 at the other end. Okay? That's why they call them gates. What goes into the gate comes out of the gate, possibly something different. Okay? That would be the truth table. These would be the values coming out. All right. Here's another tough one. How would this draw out? Okay? So I'll show you, but we should practice this. Okay? It would look like that. Okay? It's pretty straightforward, yeah. Okay? Now, here's some things that you can do with the drawing. And again, you're going to need to worry about this too much. But sometimes you have to watch out when you have lines crossing, like this. Is that where the lines meet? That little thing there indicates that they're jumping over one another. Because sometimes if you have the two lines connected, like right here, it indicates that the wires are actually wired together right there, which, as you guys know from electronics, could cause a circuit problem if the wires are actually touching one another. Okay? So it's a little bit trickier, that one. Now, when we look at the truth table, okay, some patterns start to emerge sometimes. I think one of you said, is there a pattern to this? Well, in this one, this complicated circuit, which you see here, could actually be simplified to this circuit right here, and it would do the exact same problem. So here's the bad news. Just like in regular algebra, when you can simplify an expression in regular algebra, you can simplify expressions in Boolean algebra to make them simpler. And sure enough, electrical engineers do that because it costs money to make wiring and it costs time to put more gates in place. So they want as simple a circuit as possible. So it uses less gates. It uses 3 gates rather than the 7 in the original design. And you could actually shorten it to 2 gates. If you could build a gate that looks like this. Now, this is not a gate you've seen before, but these gates exist. Gates that do and not at the same time, like an and not, or a NAND gate, not and, right? Ah, look, that's what's coming up next. The NAND and the NOR gates. So what's a NOR gate? Not or, right. So believe it or not, these gates are actually faster. You'd have to ask a physicist why, but the way it works by negating those electrical protons and stuff actually makes things go faster in that way. So NAND and NOR gates actually work faster. Now, believe it or not, you can draw a NAND gate this way, which is like not and, but because everything has a dual, not or is also the same way if you not it before you go into the or, as opposed to after coming out of the and. I don't want to over-explain that, but okay? The truth table with a NAND gate is the opposite of an AND gate, right? So it's always going to be generating 1, but at the bottom it would generate a 0. So you may remember with the AND gate, this was the exact opposite. So a NAND gate is the opposite of an AND gate. And the NOR gate, same thing. So with the NOR gate, it's going to generate only a 1 up here, and then the rest are zeros. So you may remember with the OR gate, this was going 1, 1, 1, and that was a 0. So don't overthink it too much. A NAND gate and a NOR gate basically are the opposite. They're the dual. Okay. So we can generalize this a little bit. We can say a NAND and NOR and 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 NOR gives a 1 or a 0 when both or either inputs are 1 or 0. Okay? It's basically, don't overthink it. It kind of allows you to sort of naturally work through these problems in ways. And we will look at specific IB examples here. Because again, I go maybe a little bit more deep than the IB needs you to go, because I studied this fairly heavily when I was in university. And depending on if you guys go into engineering, you might need a lot more of this sort of knowledge. Okay. I think we're going to skip through this. This is jumping ahead a little bit. Okay, here's an example. So here's a function of A and B, or A naught and C, or B naught and D. There's the circuit. Fairly complicated circuit. Okay? Here's another circuit. A and C, or B naught or D. Here's its circuit. Okay? Now, in these circuits, though, you're noticing some strange gates, though, that are actually combining 3 inputs. Here you can see there as well. Well, that's the reality, is electricians can actually build these things, too. Gates that take 3 inputs. And you can negate the outputs and negate the inputs. So life can get a lot more complicated as an electrical engineer, because now there is more variety of gates. But all of these gates are based off of the simple and or not gates that already exist. Okay? There's some more examples. All right. And then finally, we have something called the exclusive OR the XOR for exclusive. Its gate looks like this. It's a variation on the OR gate. And its symbol looks like this. It's the plus symbol with a circle around it. Now, the way it works is, it is a strange thing that looks good in a truth table. Let me see. I don't have a truth table. It gives a 1 if A is a 1 or B is a 1, but not both. So it's exclusive. If one of them is a 1, it'll give you a 1, but not if both of them are a 1. So actually, maybe let me just draw that out just slightly for you guys. I know you're starting to wear out a little bit, but let me show you what I mean. Okay? So we have X and Y and our regular OR gate. So if we have 0, 1, or so pardon me, 0, 0, 0, 1, 1, 0, 1, 1. With a regular OR gate, this is a 0, right? This is a 1, this is a 1, this is a 1, right? Because either one can be a 1 or both. But with the exclusive OR, this is what that's called, the exclusive OR. This is a regular OR. With exclusive OR, it starts off the same. That's a 0. That's a 1. That's a 1. But this one is a 0. Because the way exclusive OR works is one can be true or the other, but not both. So it's exclusive OR. Or the cool kids call it XOR. Yeah. So it's another gate that you can work into the logic, and it tends to make stuff sort of funky that way. Okay? Uses that symbol for exclusive OR. Okay? All right. There's also an exclusive NOR, believe it or not. You don't need to know that. It's not in the IB curriculum. Okay? So that's the symbol A exclusive OR B, or XOR, A XOR B. Okay? This would be A XOR B naught, which is kind of fun to say. And it negates. Okay, so what you can see here is you can actually rewrite circuit logic using XOR gates into smaller numbers of inputs. So in other words, reduce the number of gates. So the XOR gate also has been used by engineers to increase the efficiency of the computer by producing less gates to travel through. Okay, so here's an example again. I can rewrite that circuit using that. Okay, or I have a few options, different ways to write it. Okay, Here again, using the XOR gate. Oh, in this case, the XOR gate isn't the most efficient way. In this case, just an AND gate would be the most efficient way. So there's a lot of logic that can go into this, and this is not the level you guys need to go into, but I'll show you next time that there's actually laws of Boolean algebra, just like there are laws of regular algebra, that can be used to solve these types of problems. Again, it's kind of a pet hobby of mine because I studied this a lot in university. Was kind of a big part of my computer science degree was studying this Boolean algebra. I found it fascinating. It was a lot of heavy math, but it worked out pretty well. Okay, so we're going to move on. So I'm going to just jump back right to the beginning here because you guys took a lot of stuff there that kind of wore you guys out. But I wanted to just quickly show you again what the IB curriculum says. So let's go back to the beginning here. Define and or not, NAND, NOR, XOR. So if you can define those, you're good. Construct truth tables using the above. Okay? Here's the example it gives. Maria won't go to school if it's cold and raining or she has not done her homework. So maybe we've had enough for today, but next time let's see if you guys can actually do that. Write a circuit for that. Write the algebra for that. And then finally, construct a logic diagram using and or not NAND, NOR, XOR gates. Problems will be limited to no more than 3 inputs. Okay? And although I showed you the actual gate symbols, the IB will accept any symbol as long as you draw a circle with the word inside of it. So you can actually use a simpler version of that symbol. Okay? And that's it. So, one sec.